So this is the first of my, I guess, 3 lectures, and so I was going to, I know there have been a lot of motivations on hybrid quantum systems for different applications, and I see a very wide kind of community, a number of atomic physicists, which kind of surprised me a bit. But I want to talk to you about our kind of journey through hybrid quantum systems and spin-mediated optical mechanics. Basically, the notion of let's take a good old-fashioned optomechanical system that people like Keith have worked on for a long time now, and then ask the question: if I now interface this optomechanical system to a system that I know and understand very well, which is a kind of a nanokelvin gas of ultra-cold atoms that I can probe and measure and kind of manipulate in quantum limited ways, what added features or what added flexibility do I, does this hybrid system actually have? And I want to take you through that kind of a journey. And of course, this is work. The people who have really got me into this notion of hybrid quantum systems are learning about are Pierre and Keith, because I came into this very much as a cold atom person studying many body physics, maybe with some quantum optics, and then to me, solid state is, or squalid state systems are something to stay away from. Why would you want to do that? You can just study cold atoms. And it turns out there's a lot of fun stuff. But I'll try to kind of present that from my perspective as an atomic physicist. And of course, it's one thing for me to stand up here and look very important, but all the work really is done by these guys here. Watson.
So the laser pointer doesn't quite work because it's glass. So you should have to take the stick. The stick.
Oh, the matter ring. Okay. So these guys, you already they're back there. Watson, Aditya was actually a Keith student who spends most of his time. He doesn't like the weather in Pasadena. He'd much rather prefer to be in Ithaca. And Yogesh as well. Those are the graduate students, and then a large cohort of very, very talented undergraduates. And of course, like Keith was saying, these experiments are not exactly built in a week or so. They take a long time, and so for that we also have to thank these guys in blue, who were also undergraduates, who put a lot of effort into kind of giving us the infrastructure that we are now using to kind of get that science out. Okay, I guess this doesn't work.
No, this remote works. It's just a laser pointer that doesn't work. This should work. That's why experiments.
Oh, okay. In terms of it, so when I first kind of encountered the term, hybrid quantum systems, the usual kind of motivations, which to me are still very, very good motivations, are concepts like using such systems for quantum information processing or metrology, transduction between disparate degrees of freedom, either mechanical motion to spins or microwave to optical degrees of freedom, and also macroscopic quantum science in the sense of what's really going on. Think of notions like quantum measurement and measurement back action as having a huge impact on microscopic systems, single photons, single atoms, single ions, and so on. I'll talk to you a bit about that in the next lecture. But at some point, that notion kind of disappears. I mean, the fact that I'm stating at you guys does not really have a huge impact on you. You're still asleep, right? So what happens there? And, so there's a lot of questions on that transition that is of huge interest. But if I were to look at all of these and say, yeah, the motivations are great, so let's roll up our sleeves and get started. The thing you realize is, well, what you actually need to address or access such physics, you need to be able to take your system, whatever it is, and prepare it in quantum states that are actually necessary for whatever studies you want to do. You want to be able to control and manipulate the states to guide it into states that will either extract or yield the most information for the study you want to do. At the end of the day, you need to measure something. You need to be able to measure it, and like Keith was talking about, there's a lot of effort put into how you actually measure these things at the quantum level. So given all of these, once you look at this, especially as an atomic physicist, you look at these requirements, and you say, I know how to do that. Okay? And I'm standing on many kind of impressive shoulders who have taught me how exactly to do that. And the atomic physicist, the approach is very, very simple. You start by taking whatever system you have, you isolate it from everything else in the universe. So it doesn't talk to anything. And then you, once it's that isolated, it's actually very simple to cool it down to whatever degeneracy temperatures that you need to cool it down to, because you aren't competing with any kind of source of heating or dissipation. And then you develop the techniques to manipulate these quantum entities at the single quantum level, whether it be spins or whether it be photons or ions, motional states of ions and so on. And we also know how to do that. Okay? And once you have these kinds of techniques that you can cool down single atoms, cool down single ions to their motional ground states or their spin or their lowest spin states, and you know how to measure them and so on, then you start bringing many such entities together, and you say, now I'm actually doing many body physics, or now I'm actually looking at many body effects or emergent physics that arise purely from the fact that I have a lot of stuff. But I know the microscopic mechanisms at the individual quantum level. Now I'm in a great position to put things together, and that's really the kind of the bottom-up approach that characterizes ultra-cold atomic physics. And this is great. This works really, really well. So why would you want to do anything else? This is one reason why you might want to do anything else. So this is typically what it takes to this is one of our 3 machines. And as you can see, it's again, it's not built overnight. It's actually fairly complex, and that, in a sense, at some point, that stands in the way of making a lot of progress in terms of scalability, in terms of what you can actually do with the system. But to me, that is never a satisfactory scientific answer. Right? Something is hard. To me, is actually a reason to do it, not to say stay away from it. So this alone doesn't cut it. To me, a better reason is to say, well, what new physics arises from the fact that I'm merging very, very different physical systems. Okay? And those new physics also happen to be things that are actually hard to access with the bottom-up approach of cold atom physics. So one of these things is that there's a lot of proposals on how we can get very exotic many-body states like spin liquids just by this bottom-up approach of taking cold atoms, bringing them together, cooling them down to very, very low temperatures, and then creating different or engineering different Hamiltonians, and then saying, look, I have new states. Okay? And so that it's very easy. There are lots of proposals on how to do that. The problem is the very isolation that got us this far actually makes it very, very hard to get us very cold. And it's been the long-standing challenge, which sounds probably ludicrous to a non-AMO physicist, but the nanokelvin atoms that we know how to prepare and study are actually way too hot. We'd rather have picokelvin temperature atoms. Because in trying to get to nanokelvin temperatures, we made the density so small, and the density and the interactions are so weak, that the temperature has to scale down even lower. Okay? To put that in numbers, again, by the way, this is a winter school, so not a sermon, so just raise your hand and feel free to interrupt anytime you want. But if you compare, say, Fermi gas, ultra-cold Fermi gas, at say a few hundred nanokelvin, and say, isn't that cold enough? Let's compare that to a chunk of copper. The Fermi energy of that chunk is on the order of 10 to the 4 Kelvin. And you say, at what temperature, how low should I actually cool this chunk before something strange happens? Okay? Something like superconductivity. It's not 10 to the 4 Kelvin. It's 1 Kelvin. It's 3 or 4 orders of magnitude lower than the Fermi energy. So now you're talking about ultra-cold Fermi gas, which has a Fermi energy of about 100 nanokelvin. And we are stuck at maybe 20% of the Fermi energy right now. We can cool it down to maybe 20 nanokelvin. But really, you want to be at picokelvin to actually start accessing these various physics. And the third law says that as you try to get colder and colder, you better be really, really patient, because it's going to take longer and longer and longer. And at some point, nothing's perfect. The dissipate, we say it's isolated, but it's not that isolated. So so we can't. We hit a wall. We can't actually cool it down very, 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 very low temperatures. And then, in a true kind of scientist fashion, we take that problem and say, actually, it's a feature. Because now look at all the non-equilibrium physics we can do. We can look at things that are asymptotically in some steady state that is not described by the laws of thermodynamics. We look at non-equilibrium many-body dynamics, pre-thermalization, how the difference between integrable systems, non-integrable systems. So that's actually very, very exciting. And then Jorg also has a lot of efforts along those lines. The other aspect is quantum sensing. These gases need to live in a picotor vacuum chamber far from any material surface. And then you say, I'm going to sense something. The question is, well, what do you actually sense? Because it doesn't actually talk to anything. So what's the best use for it? The best use for it, or the best demonstrated use for such isolated cold gases is as a clock or a frequency standard, precisely because it doesn't talk to anything. It's a very pristine frequency standard. But there's a lot more to sense that you'd be interested in using these cold atoms to sense, but you can't, because you can't get these close to any useful surface or useful substrate. So then you say, well, wouldn't it be great if I could utilize the sensitivity of the cold gas, but interface that to some solid state surface which can actually do the sensing, and then then that information in a sense propagates to the cold gas, so I can read it out to the cold gas. So then you're saying I need the properties of the cold atomic systems are great, but really I need more. But something that more happens to be mutually incompatible with the properties of the cold gas. So then you say, now I need different kinds of systems or different kinds of properties. You need some almost a schizophrenic set of properties to do these kinds of studies. Then you say, I can't do it with one system, I need multiple systems with very different properties. And I need, ideally, find a way to merge these or interface these so that I get the strengths of both. Not the weaknesses of both, but the strengths. And the last thing I'll also touch upon, which might be a bit of a theme in the first lecture, is that the isolation is great, but really there's a lot of very, very nice challenges and physics that comes out of precisely because of the fact that a quantum system can be coupled to some kind of reservoir. A reservoir that you can tune, the fluctuation properties, make it Markovian, make it non-Markovian, turn it on, turn it off. And this notion of an open quantum system, but a tunably open quantum system is actually a very, very rich system in and of itself. Okay. And to me, these are the real motivations for starting to bring solid state systems with atomic systems. Because I get to study these kinds of open quantum systems, I get to see what new physics comes out of this, and what new things can I measure with these cold gases that I couldn't actually, or with the hybrid quantum systems that I could not previously think of. And so, in a sense, that's my definition of a hybrid quantum system. Because I searched for a while on what exactly constitutes a hybrid quantum system, could not come up with a consensus. So then that's a great opportunity for me to come up with my own definition. And so it's just a system that combines strengths of very, very different physical systems, and it's only interesting to me if new physics comes out of it. And the systems that I will show you do have such new physics, and I'll show you how that comes about from the fact that you take two systems that you might understand very, very well in isolation, you put them together, and bam, something new happens. And in the context of our group's work, we are looking at such hybrid quantum systems from the point of view of quantum enhanced sensing, macroscopic quantum measurement. I'll talk a bit about measurement and its back action and its effects on macroscopic systems in the next lecture. And then it's also another platform for such studies of open quantum systems. And so obviously you've encountered a large number of examples of such hybrid quantum systems hopefully over the course of this winter school. And I'm going to boil it all down to something canonical that we can kind of both model and experimentally realize. And to me, it's this kind of what maybe it's already conscious jargon, or maybe you introduced it. So you guys know what the membrane system is, if not I will explain it in some detail. And that's something and this constitutes an optomechanical system, and that's optically coupled to some quantum spins, which for us the quantum spins are some large ensemble of nanokelvin temperature atoms. And I'll also take you through, it's a different, to me it's a huge difference between a hybrid system and a hybrid quantum system, and I really want to kind of stress the fact that in this kind of thing, this canonical system, each particular ingredient of this canonical system is in and of itself quantum compatible, and I'll explain what that means in different contexts, and that's very, very important, because ideally at the end of the day, what we really want is to go from one phonon in this mechanical degree of freedom, coupling to one photon in this interface, coupling to one spin in this ensemble. Okay, that's really what we're trying to do. And that, in a sense, is it sounds almost a ludicrously simple thing to realize, but it's actually a very, very rich system to realize. And what does it actually take to get there? We want the mechanical resonator that is quantum compatible. In that sense, and what I mean by that is that its F-cube product needs to be larger than this ratio KT over H. I'll explain why that comes about, why that's very, very, almost a crucial requirement for any mechanical system that you want to do quantum physics with. The optomechanical system is what's known as the resolved sideband regime, which means you can isolate, you can resolve this mechanical sidebands. They're much smaller than the cavity loss rate. The spins are quantum. That's actually very easy to do, even easier for an ultra-cold for an AMO person. The temperatures are very low. You have all kinds of techniques to manipulate the spins that hark back to the days of Rabi. You can manipulate the spins in different ways because they're isolated. Their coherence times are exceedingly long, and because you have an ensemble, or you can go all the way from single atoms to ensembles of billions of atoms, you have a very large additive enhancement factor. And the nice thing is that both these systems, both the resonator, mechanical resonator, and the spins couple very strongly or fairly strongly to the optical field. And the mediating optical field, if you're good at building lasers, you can ensure the mediating optical field is only limited by quantum noise, not by classical noise. And as nice as this kind of almost Christmas list looks like, it's something that individually we have been able to realize experimentally in the lab, just by taking each isolated system, understanding what limits it, what we are actually trying to achieve, and then just building it. And these sound like theoretical abstractions, but it's actually experimentally realizable and experimentally realized. Okay. So here's the outline of what I want to do in the 3 lectures. I want to basically take each of these ingredients, the mechanical resonator, the cavity optomechanical, the spins, the cavity optomechanical system, and how this system couples the spins. And I want to go through those in kind of a step-by-step fashion. So today I'm mostly going to be talking about the mechanical degree of freedom, which we almost stumbled into as a hobby in a sense, because to me, my notion of this building this system or studying this system, this is probably the 42nd time you've heard this joke, but Pierre has this saying that physicists are either 2-level system physicists or harmonic oscillator physicists. So then you look at this and say, well, obviously this needs a collaboration.
So I also take objection to that.
He's something else then.
He's an alkali guy.
Oh, so that's a third category.
Yeah.
I see. But these are alkalis. These are alkali spins. So yeah, so it's you look at this and you say, well, you need to have. My vision was that I know how to do this very, very well. I know how to prepare these spins. I know how to control them. I know how to manipulate them. And at some point, somebody would be kind enough to give me a nice solid-state resonator, and then I'm off to the races. And then you look up the literature and you say there's companies out there which actually make for us in membrane resonators. Okay, it's just a trampoline. How hard can it be? You take some film and then you stretch it over some silicon wafer. You tap it, it moves up and down. That's a resonator. It's really not that hard. So let's do some literature searches and then say, well, I want obviously just eBay or some company probably sells these things, and I want it to be quantum compatible. So I need to just find a resonator out there whose FQ product is 10 to the 20. And then told my students, can't be that hard, go do it. And come back, and then we can study this. And it turns out that that simple system of a trampoline, everybody can access it. You can order it tomorrow with for $10. Is it? And you ask the question, then you say, fine. As a physicist, I want to understand what are the limiting dissipation mechanisms. What is the FQ product? Why is the FQ product higher? And what do I really need to do to make this quantum? It's a surprisingly hard question. And as soon as we realize that, and it's a little puzzling to me that it's a surprisingly hard question, then we were stuck because we had to study it for ourselves. We had to find the answers for ourselves, and then we found a bunch of atomic physicists starting to study, silicon nitride and silicon nitride membrane resonators and so on. But it's been a lot of fun. It's been, you kind of look at what's out there. You say, well, you start questioning everything out there. You develop new techniques for yourself. You want to say, oh, I want to measure that myself. I want to understand that myself. And very quickly, you realize that you put yourself in a kind of unique place in this community, and that's kind of, in a sense, to me, what science is all about. Okay, so that's today's lecture will be all about phonons. basically our efforts in studying these membrane resonators, what makes them work, what makes them not work, and how do we actually get to this magic regime of a quantum compatible membrane resonator while staying at room temperature. Okay. So resonators, like I said, you tap something, everything's harmonic to second order. So you tap something, it's going to move back and forth. And not surprisingly, there's a huge variety of mechanical resonators that you can access, all the way from single ions, ensembles of ions. Now it's, you take a polystyrene bead, that makes it slightly larger, but you can levitate it inside a vacuum chamber very much like trapped ions. And now again, it's a macroscopic system in a sense, but it's highly isolated from everything. So that's called like an artificial atom. Heat stuff, so this is what I would call zero dimension, 1D or nano strings, carbon nanotubes, 2 dimensions, these are still 1D in a sense. These are microtoroids which have surface acoustic modes around the rims, which can move around 5 meters. These are pioneered by Valhalla and Hippenberg. They are both optical resonators as well as mechanical resonators, so in a sense it's a very compact system to do optical mechanics. Then we go on to things like the resonators that Dan Rugar used in his original MRFM experiments, basically cantilevers with some parallel resonators. These are the silicon nitride membrane resonators that I'll be spending much of today's lecture on. And then you get to more macroscopic stuff like okay, so there's a huge variety of resonators out there. Then you say, which one should I pick? They're all pretty much equivalent, and one way of categorizing them is like what I just get this everybody knows this. Okay. One way of categorizing them is basically to say, well, what I want at the end of the day is something that couples very strongly to light, because that's going to be my intermediary. But the light field is what's going to be talking to the membrane or the resonator as well as the spins. So I want a membrane, I want a resonator that I can read off at the quantum limit, has very, very large body factors, and at the same time is strongly coupled to the light. And in a dispersive way, it's not absorbing, it's actually dispersing. Okay. And you look, I'll skip over this as well. And the most important feature, and this is what comes back to, at what point is the resonator actually quantum? The most important feature is this notion of decoherence versus some kind of interaction strength. Okay, so the resonator, unlike the atoms, is actually coupled to some path. It's coupled to room temperature, whatever the ambient temperature is, and that's why if you tap it, it brings down after a while. That's the dissipation. That's the energy going into the environment. And then you say, how fast is that? And what do you actually need to compare it to? And you say, well, I want the rate at which phonons are exchanged between the membrane and the environment. I want that rate, the rate at which a phonon pops in or out of the resonator, I want that rate to be much, much smaller than the frequency of the resonator. Or in other sense, if I plant some kind of very special mechanical state, if I imprint a mechanical state, highly quantum mechanical state on the resonator, then I want that state to live for longer than at least one mechanical period. Okay? And if you put in the math for that very simple, almost intuitive notion, what you end up with is the fact that the frequency quality factor product of these resonators need to exceed this ratio, KTO range. It's basically saying the lifetime of a single phonon needs to be larger than the period of mechanical motion. And that gives you this very, very simple FQ product requirement. And you look at this and you say, great, that explains why most people work at cryogenic temperatures, because the ambient temperature is very, very low. It also explains why the first experiments on ground state cooling of a macroscopic or mesoscopic mechanical resonator happened for resonators at gigahertz frequencies, because those are easiest to cool directly down to those are the easiest to cool directly down to the dilution bridge. So that's what Cleland did, for instance. There was no optics there, there's no optomechanical cooling. He just took a very high frequency resonator, dumped it in a dilution bridge, and then he was in the ground state. But those are highly restricting, at least to an AMO physicist, the only thing that ought to be cold in the lab are the atoms. Everything else really ought to be at room temperature. Okay? So this notion of a dilution bridge and so on is to me, a highly inefficient way of characterizing physics. So we want to stay at room temperature. So this is fixed then. We can work at very, very high frequencies, but that comes at the expense of a vanishingly small kind of manipulation time. The period is very, very low. And so you're trying to, then your interaction strengths have to be correspondingly very, very large. We don't want to do that either. So we're running out of options. So really what we want to do is to improve this. And that means getting down to nitty-gritty and saying, well, what is the limiting quality factor, or what are the mechanisms that limit the quality factor of the stress limiters? And then we went and read Marcus's review, and then there's a graph here of quality factors versus mechanical frequency for a whole range of systems, all the way from cold atoms, which surprisingly, or not too surprisingly, have extremely low quality factors, even though the temperatures are very, very low. All the way down, all the way up to the kind of stuff that Keith was talking about. I think this is Michael Tovar's work of these bulk resonators, but at millikelvin temperatures. So in a sense, this is kind of a little. I should say that some of these resonators in this graph are at room temperature, some are at cryogenic temperatures, and so on. But it gives you an idea. And given a temperature, you want to have a resonator that exceeds the quality factor. The QF needs to be larger than KT over H for that ambient temperature. So this kind of gives you an idea of, well, if this is my quality factor product, then I need to work at a temperature below a certain. Okay? And for if you want to work at room temperature, then you want a quality factor, a QF product of greater than around 6 terahertz. That's the number you're aiming for. Okay? That's somewhere between around here. So imagine a line around here, and then you say what crosses this line at room temperature, and you're basically saying not too much of that. Okay, so then you say, well, why is that the case? It's a spring, and it's something that you think Robert Hooke would have figured out how to take this up here, and you say, well, why not? And so in most material systems, there's a very, very large range of dissipation mechanisms. Ranging from the trivial, which is just viscous damping, you tap something and then there's air around it which bounces off, takes energy out. So that's then you say, well, all I need to do is put it in the vacuum chamber. There's thermoelastic damping, which basically happens in kind of bulk resonators, where I have something that's flexing back and forth, and locally the density is changing, and that causes temperature gradients between nodes and antinodes and irreversible heat flow, and that removes energy from the system. As you can imagine, that actually drops very, very, very quickly with temperature. Because at lower temperatures, the phonons become ballistic; they don't scatter off each other, and so the quality factor jumps up remarkably with lowering temperature, especially in silicon, especially in crystalline materials. Then there's radiation loss, which I'll come back to in a bit. But it's basically these resonators aren't suspended by electromagnetic fields, unlike the atoms. They're coupled to something, and that coupling can actually remove energy from the resonator. And then lastly, there's intrinsic loss, which usually modeled as something called two-level systems, TLS, and that to me is kind of a condensed matter acronym for I don't have a clue of what's going on. And so it's basically you say that there's you try to speak that ignorance with a very neat acronym. And it's probably discriminations, it's probably defects, it's I don't know what it is, but all you know is there's some phenomenological coupling between that defect and the motion of the resonator, and that somehow removes energy. And how that depends on temperature, how that depends on frequency, and so on, essentially are not very well known, but then you say you go up and measure it, and then somebody will fit it and say, I understand it. So there's all these losses, and really what the way to, it's almost, getting to higher and higher quality factors is a bit like mountaineering. You have to go base camp by base camp. You have to say, what is it at any given stage? What is the limiting dissipation mechanism? Let me conquer that. Now, of course, there's going to be another mechanism which now becomes a limiting dissipation mechanism, and so on. So we can proceed mostly by elimination. A very, very nice model of radiation loss. So most of these, viscous damping, of course, is extrinsic, but that's very easy to get rid of. You just put it in a vacuum chamber. The thermoelastic damping and intrinsic loss mechanisms are very, very material dependent. But there's another kind of loss mechanism, which is radiation loss, which is geometry intuition developed by Wilson Drake, who likened this membrane resonator here to an optical resonator. And the analogies are actually pretty close. You say, well, this is a mechanical resonator, that's just an optical resonator. There's a phonon standing wave, and if I tap this, I get all these various modes. Like this is a fundamental mode, and of course there are many, many modes. And that's just this, and I can think of that as a phonon standing wave, very much like I have an optical standing wave in this cavity. There's a range of eigenmodes, and then the mechanical dissipation is just the phonons leaking from the resonator into the substrate. And the substrate is always going to be ideally, or in most cases, more lossy than the resonator. So once the phonons escape out or tunnel out, then they're not coming back in, and that's my loss process. So that's the switch process. And the same thing happens here. The mirrors are not perfect. You put some light in, and then you switch off the light. The light is going to leak out, and you can measure that with something what we call cavity leak out. So Wilson Ray basically said, no, so now I can actually look at this as some kind of a cavity, but a phononic cavity, and then look at the way that phonons actually leak out into the substrate, never to return. And that's my loss mechanism. And that has everything to do with the way that the energy of the membrane or the resonator couples to the substrate, and not much to do with the actual material properties of the resonator itself. So in a way, to me, it's a very elegant or kind of a description of some rather ubiquitous loss mechanism, where I don't have to go into the nitty-gritty details of, well, what is this, how is silicon nitride different from silica, or issues that really don't concern me, or really don't interest me. And the other very nice intuitive picture Wilson Ray came up with is to say, well, a lot depends on the rate at which the energy goes from the membrane or the resonator to the substrate depends a lot on the actual modal geometry of the resonator. So if you were to think of the, I'm going to be talking purely in the context of membrane resonators, so just imagine some very, very thin plane or sheet under very high tensile stress. And I can characterize each of the eigenmodes by just listing the number of antinodes along the x-axis and the number of antinodes along the y-axis. So I would call this the 1,4 mode. Okay? And then a chessboard would be an 8,8 mode. Okay? So these are the nodes, these are the antinodes, nodes, antinodes, and so on. And where is the resonator actually coupled to the substrate? It's going to be along the edges. That's where it's headed. And as the membrane moves up and down, there's going to be some strain coupling between the motion of the membrane and some phonons in the substrate. And that happens entirely at the clamps. And so I can think of these antinodes around the boundary as basically radiating dipoles. Okay. So there's, it's very illustrated here. If I look at the motion of these nodes or antinodes right here, they're pretty far away from the substrate. So they're not going to contribute too much to radiation loss. But the nodes and antinodes around the periphery, they are pretty strongly coupled to the substrate. So these are probably going to dominate the loss, the radiation loss of mechanical energy from the membrane into the substrate. Okay. So now the geometry, how does the geometry come into play? If I have what I call an anti-symmetric mode, something that looks very different along this axis than along this axis, then I look at the nodes or the antinodes, say along these axes. These two antinodes are oscillating pi out of phase. So the radiated energy from these antinodes is pi out of phase. So in the far field, they can destructively interfere. Okay, so I basically have neighboring antinodes doing this. And if I look at these as dipoles, and I go into the far field, they will actually fall off, they actually destructively interfere. But this destructive interference does not, or this radiation pattern along this axis is not the same as the radiation pattern along this axis, because the number of nodes along this axis is very different. So you'd say, yes, in a sense, I should have destructive interference, but it's not that good because the modes are not symmetric. Whereas in this case, the radiation pattern along this axis, and if I go far enough along any axis, looks exactly the same. And so the interference of, or the destructive interference of radiated energy from a mode like this would be suppressed just by the geometry. Okay? So this, in a sense, is almost a self-isolating mode. It does not want to radiate energy into the substrate because that radiated energy is actually destructively interfering.
So you mentioned the destructive interference be suppressed?
Suppressed, or sorry, the radiation should be suppressed because of destructive interference. Sorry.
But it also means that the modes in your substrate should not be damped.
Exactly. So these modes.
If they're damped, they are then these interference argument doesn't work.
Right. So I'm basically saying if all the intrinsic loss mechanisms are not relevant, and radiation loss is the dominant mechanism, then if I measure the quality factor of this mode, I'll find that it's much larger than the quality factor of this mode.
Just as a radiator, as an acoustic radiator.
Exactly.
It has
Exactly.
insulation.
So basically, the first question you have to ask is, well, what is the dominant dissipation mechanism? Okay? And that, in fact, is actually a really hard question to ask because you can only proceed by elimination. Usually, there's no clear signatures of what the dominant mechanism is. But then I'm saying, look, if I see that the quality factor of this mode is much larger than the quality factor of this mode, then I know that radiation is the dominant mechanism.
Mukund, question. Is that true in the, I mean, that's true in the case where your frame for your, is nice and symmetric and everything is even. But if you have defects along the edge, then an anti-symmetric, kind of nicely canceling thing, that defect will break that cancellation, the interference, and so you could still damp out that type of mode quickly. Am I understanding this correct?
Well, what you're describing is a very, very tiny effect because at the frequencies that we are working in, the wavelengths are so large that its coupling or some kind of a Frank quantum factor of that mode to some microscopic defect in the substrate is vanishingly small.
Well, microscopic or fabrication defects. So it might
fabrication defects, again, the modes that I'm talking about have wavelengths on the order of hundreds of microns. Okay. Fabrication defects on that order, you're doing something really wrong.
Fair enough.
And what about clamping, like boundary conditions? Are those taken into account?
Yeah, that's precisely what gives rise to this. The clamping and the flexural rigidity of the membrane is precisely what gives rise to the coupling between the membrane and the substrate in the first place. Okay. If the substrate were this infinite mass system that the membrane is resting on, then just the mass mismatch is going to ensure that the radiation is actually very, very weak. Okay, so that's one thing. So it's a very nice geometrical interpretation and a signature, a very nice geometrical signature of clamping. And so just some very, very quick stuff on how we actually measure the dissipation in these structures. It's basically just a Michelson interferometer. You shine some light on the membrane, you interfere it, and then you do some Hawking detection. You get some very nice ring-down curves, and then you can also resolve thermomechanical motion. For the membranes that we study is on the order of a few hundred femtometers, and we have no problems resolving that. And what we are interested in is this ring-down. Okay? And then you can see that we get ring-downs, we get very, very Hawking functions. And so then we went off, or rather I should say Watson went off and took these resonators and did a very, very, very thorough job of looking at the quality factors as a function of the frequency of the modes. And as I said, these modes, these trampoline resonators have a huge bunch of modes with a very well-known dispersion, and the measured quality factors, or the measured frequencies agree with, when we do spectroscopy on these modes, the measured frequencies and the measured dispersion agrees with what you expect just by calculating using thin plate theory within like 0.1%. So it's very, very good agreement. And then we typically see, as we increase the frequency of the modes, we typically see a pattern that looks like this. Initially, the quality factors are fairly low, and by low, we're kind of spoiled in our group. By low, I mean the quality factors of 10 to the 6 or so. And then as frequencies go up, we get all close to 5 times 10 or 5 times 10 to the 7, 15 million quality factors, and this is all at room temperature. Okay? So 15 million at room temperature already means that we have broken this KT over H bar limit by about a factor of 20 or 30. So we are in great shape. But but that's not, it's one thing to say we are in great shape, another thing to say, well, why not a factor of 1,000 better than KT over H bar? So what is the limiting factor? And why aren't we pushing this up? And we typically see this pattern where the quality factors essentially go up and then they plateau out. And this plateau, once we get to this plateau, the quality factors are very neatly dependent on frequency. And the question now is, well, what's going on? Can we explain this, and can we then push it up even further? And as you can see, the frequencies are on the order of a megahertz or so. Oh. Again, proceeding by elimination, we said, well, is it thermoelastic damping? That's very, very easy to calculate. Turns out it's not. It's the thermoelastic damping limit for silicon nitride membranes, especially under the very high tensile stress. It would be great if we are there, but that quality factors would be on the order of 10 to the 11. We are not there. The other thing we noticed is that, and this is something that a lot of people who have studied silicon nitride membranes have noticed, and that kind of come to the wrong conclusion about, is to say at any given frequency band, I kind of previously pointed out, I said as a function of frequency, the quality factors do this, and once I'm past like a couple hundred kilohertz, the quality factors are fairly constant or very weakly dependent on frequency. But it's a different thing to say, I'm going to sit at one frequency and then enumerate the quantifactors of all the modes at that frequency. Okay. So let's look at all the quantifactors out here, and you say I have a fairly large spread of quantifactors at any given frequency. But any intrinsic mechanism should only depend on the geometry. It only depends on the local curvature. Okay, and that's more or less fixed for given frequencies. So why do we see a large spread? And most of the time, the kind of the accepted explanation was, well, there's fabrication imperfections. Okay, we can't control each and every mode. So obviously, there could be a few stragglers, something went wrong. Maybe there's a piece of lint at the anti-node for one of these modes. And so who cares? What all we care about is that there's a large quality factors out there. Okay? And we said, well, if you're sufficiently careful, we ought to be able to get rid of that. And if we can't get rid of that, maybe there's actually a very good explanation that what we really should be doing is not go in frequency and look at the top and look at the plateau here, but actually sit at one frequency and say, can we account for all the quality factors in this small pattern? One explanation is better than 15 explanations.
What's that dotted line from?
This one?
From Norris, yeah.
Okay, so this was, so there's a way to, this is also one of the things that, actually one of the early works on silicon nitride in the context of optical mechanics was actually done by Jeff Kimball, who also saw these very large quality factors. And these quality factors are actually slightly lower than what you would predict based on one model of thermoelastic damping. Okay. And just a bit lower. And so then the natural explanation was, well, obviously we're limited by thermoelastic damping because our quality factors are just slightly lower, and so everything works out. But the model that this dashed line does not take into account the very large intrinsic stress of the silicon nitride membranes. And once you take that into account, the quality factor, the dissipation scales as some third or fourth power of the intrinsic stress. And so that's actually a huge correction. And so that actually, once you take that, so this is zero stress model. And once you take into account the intrinsic stress, the quality factor goes up by about 4 to 5 orders of magnitude. And to be honest, we bought this initial explanation up until the point that we started seeing our quality factors exceeded. And then we said, well, obviously that can't be the limiting factor. And then we calculate the real limiting factor with the intrinsic stress, that's 200. Okay, so it's obviously a safe limit of it. There's something else that's limited. And so we said, okay, let's sit at one small frequency band and then look at all the quality factors. And any intrinsic model would really say, well, look, the quality factors have nothing to do with the geometry of the modes. They only have to do with frequency. So if I sit at one frequency and just look at all the quality factors, they should all line up. And so you would say, well, I expect to see quality factors that look like this. I measure instead the green dots. Obviously, intrinsic loss mechanisms are not going to work. So then we said, the atomic physicists, or at least cold atom physicists, have this kind of, we're almost used to thinking all our data ought to come in the form of nice images. If you can't image, if you can't see what you're doing, then you probably don't understand what you're doing. Okay? And so spectroscopy is great, but we want to image it. And then we said, can we actually look at the modes themselves and then deduce, show me the image of a mode, and can we come up with an algorithm that says, show me the image, and I will deduce what the quality factor is. Can we look at, it's a bit like, can you see the shape of a drum? If the answer is yes, you can. And the question is how we actually do this, because the actual motion of these membranes is rather small. It's on the order of a few hundred femtometers. So one obvious thing to do is to just say, look, we have an interferometer that can detect the motion. Now I'm just going to have my graduate students slowly scan the spot of this interferometer back and forth, realign it, and then it's going to take a few days, but they have nothing else to do, so that's great. The other way to do it would be to say, well, let's actually come up with an imaging technique that can actually resolve this very, very small motion. And as atomic physicists, we have dozens of imaging techniques under that we know how to work with. And one easy way to do this is to have something called dark ground imaging, where you shine some light off of the membrane, which happens to be inside a vacuum chamber, and then you allow and then you take the light that reflects off the substrate and use that as a local oscillator. So this is actually, even though you might have to kind of squint a bit to view this as a Michelson interferometer, it is exactly a Michelson interferometer, except you're just getting rid of the DC signal. And if that works well, and it does work well, then you're staring at images that look like this. So these are single shot images taken within a few milliseconds or so. show, of different membrane modes. Okay, that you excite different modes. You know exactly where the frequencies are, so you tap it at that frequency for a bit, you let it bring down, and as it brings down, you take these images. And you can recognize this to be the 9-9 mode, with 9 antinodes in this. And you can see the color scale, displacement for the color scale is indicated right here. So you can see this is the 9-9 mode. This would be the, I don't know, many 1 mode, or 1 many mode. Okay? And so you can see these modes and we say, great, now we have very nice images of these modes and they look exactly like what we expect. Because thin plate theory says the 9-9 mode, it gives us a frequency for the 9-9 mode, and it says, well, the 9-9 mode should have 9 antinodes this way, 9 antinodes this way. That's exactly what we see. Great. And from Wilson-Rae, and then Wilson-Rae will look at this and say, look, this mode ought to have much larger quality factors than this mode, because the destructive interference here is much better than the destructive interference. So this mode is in a sense self-isolating, this mode is not as much. Okay, great. But there are also surprises. This is not, this doesn't look like integer mode. Okay. So what's going on here? It's first you say, well, that's really pretty, but there's probably some fingerprint somewhere or something else happened, because this is not what I expect. But it is what you expect. And this is the calculation, or actually just a mathematical plot. And this is basically the 6-10 mode, 6 antinodes in this axis, 10 antinodes in this axis, hybridizing with the 10-6 mode. If you superpose 6-10 and 10-6, this is exactly what you get. Okay? And 6-10 and 10-6, from thin plate theory, those two modes are nominally degenerate. They are very, very close in energy, and they can be hybridized for some vanishingly small coupling. Okay. And then you look at it from the perspective of symmetries, you say the 6-10 and the 10-6 are not that symmetric. But the 6-10 plus 10-6 is actually very symmetric. 6-10 minus 10-6 is also very symmetric. Okay. So this hybridization between these nominally degenerate modes can actually cause the modes, the hybridized modes, to actually get a better quality factor than you would normally expect.
What is the the frequency difference between the two, the plus and the minus?
The frequency difference can be on the order of, in terms of the actual eigenfrequencies, it's probably on the order of 10 to the minus 5.
But you can excite them.
Yeah, because that's why I said in terms of the eigenfrequencies, it's 10 to the splitting is 10 to the minus 5 times the eigenfrequency.
Right.
In terms of the mechanical line width, it's 10 to the 2 or 10 to the 3 times mechanical line width. So you can resolve it really well. Okay. So the mechanical line width for the quality factors that I'm talking about are on the order of tens of millimeters. And what that also, sorry.
So what's a coupling? What does a coupling do? Is that very clarification, or is that?
It's either very, very slight strains in the substrate, and by very slight, and I was going to ask you this as well, the quality factors are so large, and it's a silicon nitride membrane resting on a silicon platform, that the thermal expansion coefficients are slightly different. And what we can actually see, if you were to watch one mode, and the temperature in the lab changes by 2 microkelvin, this mode can move, and we see that. And our lab temperature is not stabilized to 2 microkelvin. Okay. So then you say, well, if you just watch these modes, they're super sensitive to very, very, very tiny strains, differential, anything that can break the symmetry, which is what you want in a sensor. Okay. But it's nothing to say, we need to control this. And so what we actually do to stabilize it is to say, we're going to study some modes, but we're going to take some mode far away from the modes we're studying, measure its frequency constantly, and then feed back heat or cool the substrate to keep that frequency fixed. So we essentially temperature lock using frequency spectroscopy. But to answer your first question, very, very tiny, unimaginably tiny differential stresses can cause this coupling.
This is again where red sideband cooling is so helpful, right? Because you broaden things and you're less sensitive to
Exactly.
shifts.
Yeah.
Right. You start to realize it's a really important
Absolutely.
process.
Yeah. Because if you, I think you have a slightly bigger problem than us because your frequencies are much lower as well. But if you come in and your students come in the morning and say all set to detect gravity waves, and then somebody puts his cup of coffee down and that causes it ringing, it's going to ring for the next 5,000 seconds. So you might as well go home and come back, and then make sure you don't. Yeah. Lots of it, yeah. It's almost mandatory actually. Okay. So the fact is that
Have you ever seen the degeneracy of 3?
Yeah, 3, 4, yeah.
No, meaning the 3 modes hybridizing. Is that possible? This is 2 as pairs.
It could be. We haven't looked closely enough, but I'm sure it's possible. Yeah. I'm sure arbitrary superpositions are possible. And that's, yeah.
So I have actually one question. Was it intentional that you had so many modes at the same frequency or similar frequency?
So I think so. I can just write down the eigenspectrum. I kind of had a slide that I went through very quickly. But if I have some, I'm guessing you can see this. If I have some membrane, then the eigenmodes of this membrane essentially go as that.
So can you read what set the denominator?
Oh, sorry, yeah. So this is the intrinsic tensile stress. This is the length of the membrane, or the side of the membrane, rho is mass density.
Okay.
And I and j are the indices,
Right.
which quantum numbers in the sense of the number of antinodes to the two axes. So they go as I squared plus j squared to the 1/2.
That's a degeneracy.
Exactly. And so you would say, I used to know there's a 5, 6, or the earliest degeneracy happens when you have so 3, 1, and 1, 3 are degenerate, obviously, and so on and so forth. And then also, you can also have multiple degeneracies. The point is, as you go to larger and larger modes, the number of modes within it, the density of space is increasing.
Mm-hmm.
So at some point, you can have an arbitrary number of modes within some small frequency.
If you're not perfectly quadratic, you also lift this some of these degeneracies.
Yeah, exactly. But by very tiny amounts. Like I said, it's about 10 to the minus 5. The degeneracies that the splits we see are about 5 orders of magnitude smaller than the actual eigenfrequencies.
But my question is, was it intentional to have this degeneracy? Because you could have made a membrane which was inherently asymmetric, and then this is not what the mode would have looked like.
Yeah, so if you take a membrane and you really distort one axis, right? So then you can definitely imagine that you're forcibly splitting all these and making them much larger.
Yes.
Yeah.
But you wanted this degeneracy.
This actually came as a surprise, to be honest.
Okay.
But then we realized it's actually very, very important to getting very large quality factors. It's actually a feature. Okay. So the key is, once we are able to look at the modes and we identify the symmetry, then the pattern starts emerging. Okay. All we have to do is look at the quality factors within some frequency band and tabulate it as a function of the geometry. So we're going to look at this not as a function of frequency. The frequency is held fixed, but as a function of the symmetry. And the symmetry, like I said, the eigenmodes are proportional to the quadrature sum. So if I hold the frequency fixed, what it really means is I'm traveling in some arc in Mn space. Okay? That's what I'm doing. And if you plot that as a function of arc, this mess here, probably due to imperfections, probably due to fabrication, probably due to lint, whatever explanations people had, if you just tabulate them in the right degree of freedom, you see a pattern. And that is precisely the pattern, and the blue lines are precisely what you would calculate based on the radiation laws, taking into account the hybridization of the groups. Okay. So now things start getting.
What is phi?
Sorry. So the way we have plotted, I jumped a step there. The way we have plotted this is this is the eigenmodes. Call this for consistency M and N, because that's what I've used there. And what I can do is I can plot in Mn space at a given for a fixed frequency. I travel in this arc. So I can then instead plot this as a function of phi, which is tan inverse of M over N, and that will go from 0 to pi over 2. So the 45-degree angle would be the M equals N point. And so now this agrees very well. And this is kind of encapsulates the results. This is traveling in JK. Okay, I keep changing indices, but you know. So you see the quality factors are much higher here and lower here. And if you actually now use this model and repeated measurements of these new radiation cost model, then you can get a very nice prediction for the quality factors. And this is the ab initio calculation now, and that's the data. It agrees very well. And ab initio calculations, I think, are would be something you do in atomic physics, not in solid-state physics, but actually at least very, very
So, but there are some really strong outliers, right? So you see, you know, phi equals 10 or something, and then there's this, it's actually better than phi equals 45 for one or two of those points.
Phi equals 10 is, so
like right up there at the upper right-hand corner, that point is actually better than right on.
So we have actually been almost too honest for our own good in this graph.
No,
and no, the reason it comes back to saying, you're assuming that all the modes are hybridizing exactly the way you think they ought to hybridize, and sometimes, this comes back to the previous question, some of the modes that you think ought to hybridize don't hybridize. But we are still including them in this plot.
And why don't they?
Because the splitting might be slightly larger, yeah, exactly.
So I guess my question is though, so is that then the explanation for why some of these ones that deviate from the theory is just because they're not following this hybridization?
Yeah.
Okay.
But if you were to take the actual measured image that you guys have and then use that as the input.
Yeah. This would clean up really fast.
Okay.
Yeah.
Okay. That would be really a strong statement.
Yeah, I mean, to me, this already is a strong statement in comparison to, we don't know what's going on here, but we don't care. Yeah.
Is it difficult? Why is it so difficult to make more symmetric, like a pentagon membrane, pentagonal one?
And that would help you in what? I could think of a circular membrane, but a pentagon is a strange.
I don't know. I feel like it has more symmetry.
funding.
That's the reason.
I wasn't thinking of that.
For defense applications.
Or it's the membrane of the beast as well.
But why a pentagon?
I don't know. It feels like it has more symmetry, so maybe you can get more of these things.
To me, a circle would be the ultimate.
No, a circle, yes, most symmetry of a circle, but like a pentagon has more symmetry than a square.
Sure. I mean, so to me, those are geometrical factors in a sense.
Yeah.
Okay, and to me, the whole reason I was doing all of this is to understand, well, what's the limiting mechanism? And then going from a square to a pentagon to dodecahedron and just finally to a circle, that gives me some geometrical factor, but it doesn't change the underlying physics. To me, it's about, is it intrinsic loss? Then that's one way I need to think about to conquer that. Is a geometrical loss, is another way I need to think about conquering that. And then the geometrical factors come alongside. So yeah, we could, now having understood this, we could go to a circle, for instance. Sure. Okay, how am I doing on time, by the way?
You're doing, how much time do you need?
I'm halfway through. Or I can be anywhere from 1 minute away to halfway through.
Let's do 1 minute away.
Oh, wow.
Well, actually, it depends how much money do you have. 1 minute away.
Okay, fine. Okay, so I mean, this is only my first lecture, so I can
Yeah.
So the next immediate resolution is to say, well, look, this nice picture is because the membrane modes were interfering with themselves. But that's rather selective, and we are at the mercy of whatever modes that want to hybridize. But we can be more robust, or we can control things. When in doubt, we want to control things. Then we say, well, I can get the substrate to do the interference for me. Okay, so then we say we don't care what the mode is, but that mode is not allowed to radiate energy to the substrate because the modes of the substrate interfere with themselves to stop propagation. That's just exactly what you call a band gap material. Okay. And so we build this band gap, we characterize it, we can see this very nice band gap. We do the opposite experiment where we try to pump in energy from the outside and say, does that elastic energy actually go into the interior? We say outside the band gap, yes it does. Inside the band gap, that flow is suppressed. So that's exactly what a band gap is supposed to do. Yeah.
So is there some intuition of like what's going on? Like how do you choose the shape of this the substrate?
Yeah, there's the short answer is given I'm 1 minute away. The short answer is COMSOL. There's this package where you design these things and you calculate the propagating modes. So basically, you take one unit cell of these, and then you imagine an infinite plane of these unit cells, and then you say what is the dispersion relation, and then you find frequency bands where there is no mode, and then you change the parameters of this unit cell so you can place your band gap where you want it.
And then, so what even are the modes of this thing? Are these little squares that shake with respect to each other?
Yeah, exactly. Yeah. So imagine a plate. Okay, it has some propagating modes, some waves. now you start putting these divots in those plates, then what happens is that the reflection of each of these divots ends up destructively interfering the propagation of that. Okay. So it's not the modes of the unit cell itself, it's that the divots or the chunks of the gaps in the plate are causing interference in such a way that the propagation is suppressed. Okay. And when we put this, when we look at the quality factors of the substrate with this band gap, what we see is that this kind of hyperbolic dependence gives way to this flat dependence. So we have completely eliminated the geometry of the modes themselves from the problem by putting on a band gap. Again, this corroborates. We see this very nice qualitative behavior change from this to a flat line. Again, corroborates the band gap or the intrinsic loss. Okay. So now, after all of that, we can add to Marcus's graph and say this is where we are. And that. Oh, so this mechanical nonlinearities I will get to tomorrow. And so then I'll just go straight to that summary. Yeah, so these are the super Heisenberg scaling and the out of equilibrium physics I'll get to tomorrow. The nonlinearities for reservoir engineering I'll get to tomorrow. And so this is kind of where we are. So tomorrow we'll quickly go through mechanical nonlinearities, how to engineer them through reservoir engineering, and then start talking about science. Okay, thanks.
Thank you. We still have time for a few questions. Yeah? No? No. Questions, comments? Again, Mukund will be here for the duration, so don't forget to pick his brain. If there is no urgent question right now, maybe we should take another 5 or 10 minutes break to stretch our legs. Okay, thanks again.